Hello there and welcome back to the Science Sleepy Minds. Tonight, you're not standing on Earth. You're floating, weightless, on something stranger than air, stranger than vacuum. Beneath you, a vast field stretches in all directions, black as velvet, yet alive with ripples and dents like invisible footprints pressing into a trampoline. This is space-time, or more precisely the metaphor of space-time, the fabric on which the universe dances. But as you hang suspended, silent and small, you begin to wonder, what is this fabric really? Is it a thing? Is it stuff? Or is it just the name we give to how gravity behaves when we're confused? You probably won't survive this kind of philosophical free fall, but don't worry, that's kind of the point. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And as always, I'd love to know, where in the world are you listening from tonight? Drop your location and local time in the comments. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You drift in the dark, still cradled in that oddly stretchy surface, this so-called fabric of space-time. It's one of those phrases tossed around in documentaries and high school physics classes, but like so many poetic shortcuts in science, it masks a much weirder reality. Space-time isn't made of cloth. You can't thread it or tear it or roll it into a ball, but strangely we treat it like a medium, a thing that can bend, stretch and carry waves, like light. That idea exploded into physics in the early 20th century, thanks to one particular guy with famously fluffy hair, Albert Einstein. Before him, we thought space was just space, empty nothing, a grid at best, a cold, passive background across which matter moved and time ticked. Then Einstein came along and said, what if that background reacts? What if, when a planet moves, the grid shifts? What if massive things like stars actually shape the space around them? In that moment, space and time stopped being stage props and became actors, flexible, curved, and woven together. But what exactly are they made of? Here's where things get suspicious, because you, lying there, might reasonably ask, if space-time can bend, does it have molecules? If a wave travels through it, what's it waving through? And the answer is unsatisfying. At our current level of knowledge, space-time isn't made of anything, at least not in the way a bed is made of wood or air is made of molecules. It's a set of relationships, a mathematical structure, a geometry that assigns distance and duration between events. No atoms, no ingredients, just rules. That's the official story anyway, but crack open the quantum physics textbooks, the ones with all the scribbles and tear stains, and things get far more chaotic. There are hints scattered throughout black hole equations and Big Bang models that space-time might not be fundamental, that it might emerge like a mirage from something deeper, something more discrete, something below space and time as we know them. You might be thinking, okay, sure, but hasn't that idea been around for ages? Yes. In fact, way back in ancient Greece, the philosopher Democritus believed that both matter and space were built from indivisible units, atoms and voids. He imagined the universe as a cosmic game of Tetris, made from blocks too small to see. Fast forward 2,000 years, and weirdly modern physics might agree with the guy. Because when you zoom in far enough, smaller than atoms, smaller than protons, down to what's called the Planck length, about 10 to the power of minus 35 meters, the smooth fabric of space becomes fuzzy. Not literally fuzzy like your favourite blanket, but uncertain, unstable, and blurry in a quantum sense. Down there, distance loses meaning. Time gets slippery. The whole notion of a location starts to break. It's what physicists call quantum foam, a boiling mess of maybes and may not be's. We'll dive into that more in, but here's the spooky thing. If space-time becomes nonsense at small scales, then maybe it's not as real as we think. Or maybe it's real the way a rainbow is real, visible, measurable, but not a thing you can hold in your hand. Mainstream physics still holds the line, Spacetime is geometry, not stuff. But increasingly, theories suggest there may be something beneath, a hidden layer, a discrete structure. Maybe it's digital, maybe it's relational, maybe it's made of information itself unfolding as the universe evolves. Of course, historians still argue whether the concept of a space-time medium ever made sense in the first place. Some say it was always just a metaphor. Others think we're on the verge of uncovering an actual lattice of reality, an ether of a new kind. Not the ghostly wind that 19th century physicists believed carried light, but a deeper scaffolding, invisible and unknowable, yet always there. Then again, it could be that asking what is space-time made of is like asking what's the number 7 made of. You can describe it, use it, even see it in action, but you'll never pull it out of a drawer. Maybe space-time is just the way the universe keeps score, a tally of how things relate, not a field of pixels we can poke. Still, the human brain doesn't love abstraction. We crave pictures, textures, stories. And so, the idea of a fabric persists. We picture stars sinking into it like bowling balls on a trampoline. We imagine waves, gravitational ones, rippling across the void like sound through air. These metaphors help us teach. They help us sleep at night. But tonight, as you hover quietly in your imagination, you start to sense the limitations. You realize you're lying not on a surface, but on a concept. And beneath that concept, something else might lurk, something less poetic, something more pixelated, something that's been waiting to be found. You're still floating, but the space around you starts to tilt, like a slow-motion dream where everything slides sideways. That stretch of black velvet you imagined, space-time, is beginning to warp. Not metaphorically, not poetically, literally. Right now, in this thoughtscape you've drifted into, an enormous object has just appeared beside you. Let's call it Jupiter. That'll do. As Jupiter settles beside you like a giant sleeping marble, the space-time beneath it dips, deeply. You, being nearby, slide ever so slightly toward the depression it causes. It's a bit like when your cat walks across your bed and your pillow tilts just enough to knock your phone onto the floor. Except here, the phone is a planet, and the bed is reality itself. Welcome to Einstein's favourite visual aid, the rubber sheet. This is how most people first meet the concept of general relativity, a stretched out 2D sheet with heavy balls placed on it to show how mass curves space-time, and it is helpful. It gets across the general idea that gravity isn't a force pulling things like a magnet, but rather the effect of masses following curved paths through a distorted geometry. But here's the thing, that metaphor breaks badly when you actually start asking questions. For example, what exactly is that rubber sheet sitting in? What dimension is that? And why does the ball sink in the first place? Because gravity is pulling it down. But gravity is the thing we're trying to explain, remember? If the metaphor needs gravity to explain gravity, we're kind of in trouble. Plus, the universe isn't a 2D sheet. It's 4D space-time, 3 dimensions of space, and 1 of time, blended together in ways that are truly dizzying if you stop and think too hard, which obviously we're going to. Einstein's equations describe how energy and mass tell space-time how to curve, and curved space-time tells matter how to move. It's elegant, almost suspiciously elegant. And in the 100+ years since those equations were published, they've passed every test we've thrown at them, predicting the orbit of Mercury, the behaviour of black holes, the way time slows down near GPS satellites, and even the gravitational waves that ripple through space when 2 massive objects collide. But here's the catch. These tests happen at big scales, planet-sized, star-sized, galaxy-sized. Once you start shrinking things down to the tiny quantum realm, general relativity starts sweating profusely and mumbling into its napkin. Because at small scales, reality doesn't behave like a smooth sheet. It gets chaotic, random, jittery. You can't keep using curved geometry to describe a place where the geometry itself might not exist anymore. This is the edge of the metaphor. the point where the nice trampoline stops being useful and starts being a distraction. There's a famous story, quirky and true, as far as physicists' bar conversations go, about Richard Feynman, the Nobel-winning quantum mechanics maverick. He once reportedly grumbled that no one really understands general relativity, not because the math is hard, though it is, but because the conceptual leap, treating time as a dimension that curves, breaks our brains a little bit, especially when you try to reconcile it with quantum theory. And speaking of awkward brain stretches, here's a historical gem for you. Back in the early 20th century, some physicists clung to the idea of the luminiferous ether, a medium that supposedly filled all of space and carried light waves the way air carries sound. But after Einstein and the famous Michelson-Morley experiment, that idea got tossed into the cosmic recycling bin. Still, maybe it shouldn't have been, because now, over a century later, some physicists are quietly whispering the A word again. Not that A word, this one's ether, but this time it's not a ghost wind made of spiritual fog. It's something deeper, maybe quantum, maybe geometric, maybe computational, because if gravity is geometry, then what's the geometry made of? Historians still argue whether Einstein himself thought of space-time as a substance. In some writings, he seems to imply it's just a mathematical abstraction, a coordinate system. In others, he uses more suggestive language. He speaks of space-time having a kind of physical reality, something that can possess energy and interact with mass. And in his later years, he famously pursued a unified field theory, hoping to blend gravity and electromagnetism into a single framework, suggesting he did think there was more going on under the hood. The rubber sheet is a stepping stone, it's not truth. It's a visual shortcut to get us used to the idea that space isn't passive, that it can bend, that it responds to mass. But the deeper you go, the less useful the metaphor becomes. Picture this. Instead of a sheet, imagine a dynamic, constantly updating matrix, a 4D chessboard whose tiles shift based on who's standing where, when, and how fast they're moving. Objects don't just sink into the board, they reshape it moment by moment, and maybe, just maybe, the board isn't made of anything at all, until something interacts with it. That's where things get slippery again, because we're still not sure if space-time is a background or a consequence. Is it a thing we move through, or is it a pattern that emerges from our interactions? There's an even weirder idea coming down the pipeline, that gravity, the whole reason we use the rubber sheet analogy in the first place, might not be a fundamental force at all. Some physicists believe it could be an emergent property, a kind of statistical effect like pressure or temperature that arises from something more basic. Quantum entanglement, perhaps, information flow, relationships, not particles. If that's true, then the metaphor needs to go. No more rubber, no more sheets. Just a complex twitching network of stuff we don't yet understand, which only looks like curved space-time when seen from far away. Still with me? Good. Because next we're going to fall even further, down into the bubbles, the boiling chaos, the foam that fizzes at the bottom of the universe's bathtub, where nothing stays flat, nothing stays still, and space itself starts to lose its mind. Pack your quantum snorkel. The deeper you drift, the less the universe makes sense in the ways you were taught to expect. You've left behind the neat elegance of Einstein's smooth curves, that tidy idea of planets gently sinking into space-time like marbles on a blanket. Yeah, no, that's been shredded and tossed into the theoretical trash compactor. Now, as you dive past atoms, past the quantum fields, past even the ghostly mist of virtual particles, you begin to reach a place where space-time itself fizzes. It doesn't roll or stretch or ripple here, it churns. Beneath the surface, space-time isn't smooth at all. It's more like a cauldron of frantic quantum fluctuations, blinking in and out of coherence so fast you can't tell if they're real or just a trick of perception. This is the Planck scale, where distances are so small, about 10 to the power of minus 35 meters, that even the concept of where or when begins to fray. Welcome to quantum foam. Picture this. At these unimaginably tiny scales, the very structure of space is thought to become unstable, not because something broke, but because uncertainty is baked into the cake. You've heard of Heisenberg's uncertainty principle, right? The idea that you can't precisely know both a particle's position and momentum at the same time. Well, here, even space itself doesn't have a clear location. It jitters, it hops, it spontaneously spawns tiny wormholes, closed loops, and bizarre curvatures that collapse before they ever fully form. It's like watching a pot of boiling water, but the pot is reality. The term quantum foam was coined by John Wheeler, one of those delightfully wild physicists who somehow made it respectable to speculate about wormholes, black holes, and even time travel, long before it became cool. Wheeler proposed that at the Planck scale, space isn't a fixed, continuous thing. Instead, it's grainy, irregular, and constantly shifting in bizarre, probabilistic ways. And here's the weird part. While we can't directly observe this foam, it's way too small, many physicists believe it's there, hiding beneath the observable world like a secret pattern in a magic eye painting. The implications are massive. If space-time is frothy at the smallest scales, then maybe it isn't fundamental. Maybe it's made from something else, something discrete, something pixelated. Think about a digital photo. Zoomed out, it's smooth and lifelike, but get close enough and you see the individual pixels, blocks of colour, nothing more. Is reality like that too? From far away, it looks continuous, but maybe, close up, it's made of tiny units, quantum bits of space and time. Fringe? Maybe, but not nearly as fringe as it used to be. Several modern theories are built around this idea. One contender, loop quantum gravity, takes it seriously. It proposes that space is made of finite loops, woven together like an invisible basket. These loops form a network of spin values, called a spin network, that define the structure of space at the tiniest scales. Time? That's just change happening in this network. In this view, space doesn't curve, it quantizes. It's a massive departure from Einstein's geometry. But loop quantum gravity has been picking up attention because it might offer a path toward that holy grail of physics, reconciling quantum mechanics with general relativity. Now, to sprinkle in some historical seasoning, in the late 1940s, a lesser-known physicist named Pascal Jordan, yes, of Jordan matrices fame, wondered aloud whether space-time could emerge from something even more basic, perhaps even numbers. His ideas didn't get far back then, but now we're inching back toward that kind of thinking. That maybe space-time is an output, not an input. And here's where things get especially deliciously strange. Some researchers suggest that these quantum fluctuations at the Planck scale could actually be where gravity is born. Not a force emanating from mass, but a result of how information is stored and entangled across these foam-like microstructures. In other words, gravity could be an emergent effect, like the froth on a cappuccino, a byproduct of deeper processes. But remember, this isn't settled science. Historians and theorists still argue whether quantum foam is a literal thing or just a convenient placeholder for our ignorance. It's possible the foam is real, tiny and buzzing with wormholes like microscopic Swiss cheese. Or maybe it's just a temporary metaphor until something better comes along. Either way, if you're lying there hoping for certainty, sorry. At these depths, you'll find only questions stacked inside riddles, all wrapped in Planck scale origami. Still, here's a fringe tidbit for your collection. Some theorists think quantum foam could allow for spontaneous baby universes, tiny offshoots of reality that bubble into existence for a fraction of a second, then wink out, or possibly expand into full-fledged alternate realities. Imagine that. Entire universes born and destroyed in the space of a moment, too small for anyone to ever detect. Are they real? Are you one of them? No one knows. The equations don't rule it out. And that, frankly, is terrifyingly delightful. So as you float here, brushing your imaginary fingers along the jagged edges of space-time's foam, you realize something profound. Space is not empty. Not even close. It's a storm of fluctuations, all humming with potential, all whispering, this is not the bottom, not yet. Because underneath this churning chaos, there might be something even stranger, a code, a pattern, a logic that gives rise to the foam and in turn to everything else. And wouldn't you know it, there's a theory for that too. But first we need to go flat. Flat and fake. You blink, or would if your eyelids could follow you into this abstraction, and suddenly the churning quantum foam beneath you starts to stretch. It flattens, not into calmness, but into something far more unsettling. Imagine the entire sky, the galaxies, the dark matter scaffolding, all compressed into a two-dimensional surface, as if the universe itself has been pressed like a flower between the pages of an invisible book. This is not a visual illusion. This is the holographic principle. You stare up or down, it's hard to tell direction here, and you begin to suspect something awful. Maybe everything you've ever known, every movement you've made through space, every heartbeat was just a projection, a shadow on a wall, a higher dimensional puppet show cast onto a lower dimensional screen. And the kicker? Some physicists think that might actually be true. The holographic principle proposes that the entire three-dimensional universe, plus time, might be a kind of hologram, an emergent illusion projected from information stored on a 2D boundary. Think of a DVD, okay, retro, or better yet, one of those holographic cards that change images as you tilt them. What if you are the tilt? Now, before this starts sounding like some dorm room philosophy session, bro, what if we're just like light? It's worth knowing this idea comes from serious places, black holes to be specific. Let's rewind to the 1970s, when physicist Jacob Bekenstein made a provocative discovery. The amount of information, or entropy, that can exist inside a black hole isn't proportional to its volume, but to its surface area. That was weird. We usually think of volume, how much space something takes up, as determining how much information it can hold. But black holes seem to say otherwise. Stephen Hawking reluctantly at first agreed. His calculations showed that black holes radiate energy, now called Hawking radiation, and that this radiation carries away information. But if the info was encoded on the surface of the black hole, that meant the 3D inside wasn't the fundamental reality after all. In 1997, physicist Juan Maldacena formalized this idea in the context of string theory, with a concept called ADS/CFT correspondence. Don't worry, we'll break that down. But the short version? A full universe with gravity, like ours, might be mathematically equivalent to a lower dimensional universe without gravity on its boundary. A hologram. A reality painted on the edges, with depth and texture as illusions. You're probably feeling a little robbed. Understandable. After all, if the world is a hologram, what does that make you? Just light bouncing off an invisible wall? Well, maybe. Or maybe you're something even weirder, a pattern encoded on a faraway surface, whose echoes dance through a simulated third dimension. Historians still argue whether the holographic principle is a description of all reality, or just certain kinds of space, like anti-de Sitter space, which, spoiler, our universe is not. But even if it's only true in idealized conditions, it still hints at something monumental. Space-time and gravity might not be fundamental. They might emerge from more basic ingredients, namely information. That's right, not particles, not energy, bits. The same way a high-res image on your phone is just a series of zeros and ones that light up pixels in the right order. Your very existence might be a pattern of data points, projected into 3D experience by laws we barely understand. There's a fringe idea, still debated, that the universe's storage capacity is limited not by how big it is, but by its outermost boundary. Kind of like saying you can only fit so much detail into a painting, no matter how deep the scene appears. This brings us to another quirky tidbit. Some versions of this theory imply that the entire observable universe could be encoded on a surface just a few dozen light years across. That's it. All your memories, your mistakes, your midnight cravings, projected from a shell you'll never see, but might be written on right now. Weird? Absolutely. Comforting? Not remotely, but compelling? Oh, very much so. Even stranger, recent work in quantum gravity suggests that entanglement, the spooky action at a distance that Einstein famously hated, might be the stitching that holds the hologram together. Imagine the universe not as a place, but as a tightly woven net of relationships, each one encoding information that determines how reality feels from your vantage point. So what is the hidden layer beneath space-time? If the holographic principle is true, it's not below you, but beside you, or outside you. Not a layer like rock under soil, but like code behind a screen. You're not in a place. You're inside a computation. A tapestry of entangled states that trick you into believing you're strolling through a park, or watching the sunrise, or listening to a science video while curled up in bed. There's still no consensus on how far this rabbit hole goes. Some physicists treat the holographic idea as a mathematical convenience. Others treat it like a revelation. And a few quietly admit it could mean that everything we thought was real, space, time, motion, is just a kind of mental model that helps the universe organize itself. One last thought to keep you company tonight. If the universe is a hologram, and you are just a projection, who's watching? Who, or what, is standing outside the screen? No one knows. Maybe there is no outside. Maybe the code is self-interpreting. Maybe the universe is dreaming itself. But wherever the projector lives, it's casting a very convincing image. And you're part of the pattern. Next up, what if space-time isn't even the main event, but a side effect of something deeper still? Still adrift in this not quite a universe, you begin to notice something subtle and strange. The space around you doesn't feel like it's holding you anymore. It's not supporting you like a floor or surrounding you like a fog. Instead, it feels more like a whisper, a consequence, a side effect. The thought creeps in. What if space-time isn't the foundation of reality at all? What if it's a shadow cast by something deeper? This is the unsettling heart of a growing idea in theoretical physics, that space-time itself is not fundamental, but emergent. It doesn't exist first and give rise to particles and forces. It's the other way around. Perhaps particles, fields, and especially quantum entanglement knit together the illusion of a smooth, continuous space and time. If that makes your brain itch, congratulations. You're starting to think like a theoretical physicist. The notion of emergence isn't new. In fact, it's how most of reality works. Temperature, for example, isn't a thing at the level of individual atoms. It's a statistical effect. How fast a lot of particles are jiggling on average. No single molecule has a temperature, but a crowd of them, suddenly you've got heat. Some physicists are starting to suspect that space-time is the same way. That's the punchline of a mind-bending theory championed by people like Mark van Ramsdonk and Brian Swingle. Their work suggests that entanglement, those mysterious quantum connections between particles, might be the stitching that gives rise to space-time itself. Not metaphorically, literally. Imagine that the universe is a vast web of entangled quantum bits. Where there's more entanglement, space feels close. Where there's less, space stretches thin. No entanglement, no space-time at all. It's like saying the geometry of the universe isn't built out of distance or dimension, but out of relationships, connections, links in an invisible network. The more tangled the network, the more space there is between things. Which means the room you think you're lying in right now, that might just be a highly entangled zone in the cosmic network. Not an actual room, but a dense region of interconnected quantum threads, arranged in such a way that it feels like a cozy, familiar three-dimensional space. Think of it as the social network version of physics. Here's a fun analogy. Imagine a crowd at a party. Everyone's chatting, mingling, exchanging gossip. If you map who's talking to whom, you can draw a web of relationships. Now imagine that web as the actual space. The more people are connected, the closer together they are in the geometry of the universe. The room isn't a background, it's the result. And yes, this is the part where someone inevitably brings up the matrix, but don't worry, we're not going full simulation yet. This isn't saying we're inside a computer, though some theories do go there, but rather that what we perceive as geometry, distance, and even time may be tools created by a deeper, more abstract layer of physics. Tools that arise after the entanglement has already done its thing. Historians still argue whether the idea of space-time as emergent was truly born with quantum gravity research, or whether hints go all the way back to philosophical grumblings in the 19th century. Ernst Mach, for instance, suggested that inertia might arise from the interaction between an object and the rest of the universe, not from an absolute space. Einstein was famously inspired by Mach's ideas, but the modern twist. Maybe all of space arises this way, from relationships, not coordinates. Of course, not everyone agrees. This isn't textbook physics yet. It's still a frontier, hypothetical, highly mathematical, and a little bit squishy. But that hasn't stopped it from producing some stunning thought experiments. One such idea is that black holes, the ultimate mystery boxes of physics, might be the key to understanding how space-time emerges. Inside a black hole, classical space-time breaks down. There's no real geometry, no reliable passage of time, and yet from the outside a black hole has a perfectly measurable surface, the event horizon, with a well-defined amount of entropy. That entropy, some theorists say, could represent the number of entanglement links hidden in the quantum foam beneath. Not metaphorical links, actual quantum connections that build the black hole's space from scratch. If that's true, then every black hole is a kind of holographic data crystal, and the smooth space around it is just an emergent byproduct of its hidden, tangled guts. Here's a fringe tidbit for your insomnia collection. There's a theory that the early universe, right after the Big Bang, was not just hot and dense, but non-geometric. That means space didn't exist yet. Not even time, at least not as we know it. Instead, the universe was a roiling soup of entanglement patterns which eventually cooled and froze into the kind of geometry we can understand. Space and time, in this view, are like ice crystals forming on the surface of a lake. Beautiful, structured, but utterly dependent on the underlying water. And you're a ripple on that frozen surface. Not something in space-time, but something space-time is made from. It's unsettling, sure, but also liberating. If space-time is emergent, then it's not the ultimate limit. It's not the final floor. There's something else, beneath, before, within. A layer that doesn't care about meters or seconds. A layer that might be pure logic, pure relationships, pure structure. And that structure might not even obey the rules of space or time. You could be connected to something billions of light years away, not because light travelled there, but because the entanglement is built in. It makes sense in a way. Reality doesn't start with space. It starts with rules, with order, with connection. Space-time is just how those connections feel to creatures like you, drifting through them and calling it up and down and Tuesday. So the next time you look up at the stars or feel the floor beneath your feet, remember, that might just be the surface tension, the crust, the visible part of a much stranger, much more relational phenomenon. And you're not moving through space, you're moving with it. Because space doesn't come first, connection does. Everything feels quiet now. Not peaceful exactly, more like the silence before you realize something is terribly, exquisitely wrong. You lie motionless, but the space around you breathes, not with air, with something deeper, something invisible yet infinitely connected. It's like you've become aware of a net you didn't know you were caught in. This is where entanglement enters the scene, not just as a quantum party trick, but as a possible foundation for everything. If space-time is a side effect, like we whispered in the last section, then this, entanglement, might be the ghostly scaffolding holding the illusion together. You've heard of quantum entanglement, right? That eerie phenomenon where two particles, no matter how far apart, seem to share information instantaneously. Measure one, and the other knows instantly, even if it's on the other side of the galaxy. Einstein hated it. He called it spooky action at a distance. But experiments have confirmed it again and again. Spookiness is here to stay. But what if entanglement is more than a weird quirk? What if it's the glue that binds the universe? Not metaphorically, literally. Picture the universe not as a vast space filled with particles, but as a cosmic web. Each particle isn't isolated, it's entangled with others. And these connections define proximity, not by physical distance, but by how deeply things are quantumly entwined. This isn't just spooky, it's structural. Here's a helpful and kind of adorable analogy. Imagine you're at a massive dinner party. The seating chart isn't based on geography, it's based on who's best friends with whom. If you're deeply connected to someone, you're seated right next to them. If you're not, you're way across the room, even if you were technically closer by foot. That's what the fabric of space-time might be doing, building geometry out of friendship bracelets. There's growing evidence that entanglement patterns determine geometry. That is, the way space curves, stretches, or even exists at all could depend on the quantum relationships between parts of the universe. If two regions are highly entangled, space seems to stitch smoothly between them. If they're not, a void, a rupture, a place where space-time itself may not exist. This flips everything upside down. Usually we think of things being far apart in space, and then possibly entangled. But what if it's the other way around? What if entanglement defines the distance? Closer in quantum terms equals closer in space. No entanglement equals no bridge. In fact, some physicists have taken this idea to its most literal, fascinating extreme. They suggest that even black holes, those enigmatic cosmic stomachs, may actually be built from entangled pairs of particles. That every particle that falls in becomes part of a vast, tangled network that stitches together the event horizon and defines the space within. Now here comes the fringe flavour. Some physicists believe that wormholes, those hypothetical shortcuts through space, are nothing more than highly entangled systems. There's even a catchy phrase for it, ER equals EPR. That's shorthand for Einstein-Rosen bridges, also known as wormholes, and Einstein-Podolsky-Rosen pairs, also known as entangled particles. The idea? Wormholes are entanglement, just in geometric disguise. If that's true, then all of space-time might be woven together from invisible quantum threads, billions upon billions of them. Some tight, some loose, all shifting second by second. You're not walking across a floor, you're dancing across an unseen web, spun from correlations you'll never observe directly. Historians still argue whether this perspective redefines space-time or just reinterprets it. Is this a true physical structure, or a useful metaphor for complex mathematics? It's still hotly debated, but the math is pointing toward a bold conclusion. If you remove the entanglement, space stops making sense. The structure crumbles, not just the matter in space, but the very grid itself. Here's a quirky tidbit. There's speculation that consciousness, your actual experience of being you, might emerge from quantum entanglement too. It's extremely speculative and bordering on sci-fi, but some researchers think that brains might use quantum processes to knit together a unified sense of self, which means the same force that holds atoms together and possibly builds space could also be holding you together. Sleep tight. But there's more. Entanglement also plays tricks with time. Experiments in quantum teleportation show that entangled states can transfer information without sending it through space. There's no signal travelling. The link is already there. It doesn't matter where the particles are. The distance becomes irrelevant. That's spooky enough. But what happens when you realise this applies not just across space, but across space-time? In quantum gravity research, especially in the study of holographic dualities, entanglement seems to encode not only spatial structure but temporal structure too. The flow of time might not be fundamental. It might be a narrative told by entanglement evolving in a certain pattern. The ticking of a cosmic clock built not of gears, but of correlations. This raises a deeply bizarre possibility. What you perceive as time moving forward may just be the reconfiguration of the entanglement network you're embedded in. Time isn't flowing. The structure is just updating. That moment you just lived, it's a change in connections. The next one? A new pattern. Tick, tangle, tick, tangle. In this view, you are not a being in time. You are a moving ripple in the entanglement structure of the universe, a shifting pattern in the net. Nothing touches you directly, but everything affects you. Gravity, distance, motion. They're all re-expressed as shapes and flows in this invisible framework. So tonight, as you lie there, flesh and thought, memory and muscle, know this. You're deeply connected to everything. Not spiritually, though maybe, but physically, quantumly. The particles in your brain are knotted to particles across the cosmos. You're not separate. You're a node, a tangle. The hidden layer beneath spacetime may not be a place. It may be a network. And you've always been part of it. There's a moment, still and crystalline, where you feel like you've fallen out of space entirely, not into emptiness, but into something quieter, more mathematical. The connections you've been drifting through don't look like threads anymore. They feel like shapes, not physical shapes, but the kind you can't quite picture. Curves without surfaces, angles that break your intuition. You've just tumbled into the idea that geometry itself might be the true engine beneath reality. Not the kind of geometry you suffered through in school. No dusty triangles, no calculators. We're talking about living geometry. Geometry that shifts. Geometry that builds the universe the way DNA builds cells. Because what if the hidden layer beneath spacetime isn't a thing or a substance at all, but a relationship between shapes? It's a deliciously old idea with an aggressively modern twist. You see, ever since Pythagoras told everyone that all is number, before probably being murdered by his own cult for breaking a dietary rule, fun fact, philosophers have tried to reduce the universe to math. But in modern physics, this obsession with numbers has evolved into an obsession with geometry. Because geometry isn't just about describing the world, it might be the world. Let's start with a gentle example, the way Einstein's general relativity describes gravity. Remember the trampoline metaphor from earlier? That came from his realization that mass curves spacetime, and that curved spacetime is gravity. That's pure geometry. Mass tells spacetime how to bend. Spacetime tells mass how to move. It's all about shape, no force, just curves. But quantum physicists weren't satisfied. They started asking, what happens if we quantize space itself? What if we stop treating it as a continuous surface and instead break it into chunks, nodes, links, and loops? That's where theories like loop quantum gravity came in, saying that space isn't infinitely smooth, it's granular. Each chunk has a certain size, a certain orientation, a spin. These aren't particles, they're geometric building blocks. Space might be made of little bits of geometry, and then things got weirder, much weirder. In recent years, physicists have proposed that certain geometric structures, far removed from anything we've ever seen, might generate the laws of physics as we know them. One such structure, known as the amplituhedron, yes, that's a real word, was introduced to simplify the math behind particle interactions. But in doing so, it raised a haunting possibility. Maybe particles, forces, even space-time itself are all projections of a higher dimensional geometric object. Think of it like this. You're a shadow on a wall, and the real object, the true you, is something incredibly complex and geometric, living in a realm with no time, no space, just pure relationships between angles and volumes. Not a very cozy thought, but compelling. Historians still argue whether these geometric theories are physical models or just brilliant math tricks. But one thing is clear. The universe is suspiciously good at hiding its secrets in geometry. From the shape of orbits to the curvature of light around stars to the very shape of the universe itself, it's all geometry. Even the Big Bang, that opening note of the universe's cosmic symphony, may have been a transition from one geometry to another. Some theories suggest that before space-time as we know it existed, there was a primordial geometric phase where nothing had direction, or even meaning. Then somehow something cracked, and out came dimensions, time, space, the whole tangled mess. Here's a quirky morsel for your sleepy brain. In some formulations of quantum gravity, geometry itself can fluctuate. That is, the shape of space isn't fixed, it's probabilistic. You could say that right now, the floor beneath your bed has a well-defined shape, but at a quantum level it's shimmering through countless tiny variations. Reality might be vibrating between geometries too fast for us to notice. And that means the stability you feel, solid walls, straight lines, the reliable height of your ceiling, might just be a kind of statistical illusion, a stable average across a sea of microscopic spatial chaos. But here's the kicker. Geometry doesn't just describe the world, it controls what's possible. If you change the geometry, you change the physics. Imagine a world where parallel lines don't stay parallel, where the angles of a triangle don't add up to 180 degrees. That's not just math class gone rogue, it's non-Euclidean geometry, and it's what actually describes our real, curved universe. The kind of geometry that lets black holes exist, that allows wormholes to form, that bends light, bends time, and possibly even births universes. And this brings us to a powerful realization. The geometry of space is not a background. It's a player. It can evolve, interact, react. And maybe it can be constructed. If space-time emerges from quantum entanglement, as we said before, then perhaps geometry emerges from entanglement patterns. Or maybe geometry and entanglement are two sides of the same weird, hyperdimensional coin. Physicist Max Tegmark once proposed that the universe might be a mathematical structure, not just described by math, but made of it. That we exist not as matter or energy, but as nodes in a self-consistent mathematical object, living geometry. And you? You're a tiny, fleeting curvature in that object, a local distortion, a blip in a higher space, not a person in a room, but a ripple in the shape of possibility. Still with me? Good. Because up ahead are wormholes, quantum tremors, and the fractured seams where geometry goes completely haywire. The hidden layer beneath space-time might not just be made of strange math, it might be math. Living, shifting, shape-based math. And once you see that, it's hard to unsee it. Geometry is no longer just about lines and circles, it's the choreography of the cosmos. And tonight you're part of the dance. The air, or whatever passes for it in this abstract not place, shivers. Something has torn, not ripped exactly, but folded in the wrong direction. You're no longer floating calmly on curves and surfaces. Now you're sliding along the seams. You've found a wrinkle in the universe. Or more accurately, the universe has wrinkles in you. As you drift along the folds, the soft geometric logic you've been gliding through begins to tremble. It's not just shapes anymore. It's rips, tunnels, shortcuts. The rules of normal space start to stutter, and through those glitches come glimpses of something very, very strange. Tonight you're sliding into the heart of space-time's seams, the edges, the tears, and the quantum stitches that might hold, or fracture, the whole thing. Welcome to the world of wormholes, foam, and what might be the actual architecture of the hidden layer beneath reality. Let's start small, and I mean really small. You remember quantum foam from earlier, the boiling chaos beneath the Planck scale, where space-time flickers like a bad TV signal. Well, buried inside that foam may be more than just random jittering. It may contain tiny wormholes. These are not sci-fi portals for interstellar adventure. They're not even the kind you could slide a subatomic particle through, let alone a spaceship. They're quantum shortcuts, tiny fleeting tunnels that pop in and out of existence, possibly connecting distant points in space or even time. Physicist John Wheeler, the guy who also gave us black hole as a term, first proposed this picture, that the very fabric of space-time isn't smooth at all, but riddled with microscopic tunnels and bubbles. That at the tinier scales the universe looks less like a sheet and more like Swiss cheese that's having a panic attack. We can't see these wormholes directly, but their existence would explain certain puzzles in quantum theory. For example, how can entangled particles know about each other instantly? Maybe they're connected through these invisible fluctuating bridges, seams in the cosmic fabric. In fact, as we teased in the last section, there's a growing belief that wormholes and entanglement might be two faces of the same strange coin. This is the ER equals EPR conjecture, the idea that Einstein-Rosen bridges, wormholes, are equivalent to entangled quantum states, Einstein-Podolsky-Rosen pairs. In plain terms, if two particles are entangled, maybe they're connected by a microscopic wormhole, not a tunnel you can travel through, but a stitch in the hidden layer, a seam. This is a radical idea, but it has elegance going for it. Instead of treating entanglement and space-time geometry as separate phenomena, it unifies them. It says this connection is physical. Even if it's not made of stuff, it's just as real as any object. Historians still debate whether Wheeler's quantum foam was ever meant to be literal or just a poetic metaphor. He was a big fan of dramatic phrasing. But modern theories like the ADS/CFT correspondence, we're getting closer to that soon, give mathematical backing to the idea that space-time might be full of wormhole-like structures, some microscopic, some perhaps not so small. In fact, there are theoretical models of traversable wormholes that don't require exotic, impossible matter. Under the right conditions, and with a generous sprinkle of quantum fields, it might be possible to engineer one. Not now, not soon, but perhaps in the far future. Or, if you're feeling conspiratorial, in a galaxy far, far advanced. But let's get weird. There's a hypothesis, hanging out on the fringe, that space-time is literally stitched together from microscopic wormholes. That the continuity we experience, the feeling of motion from one point to another, is built on a vast underground network of these invisible seams. You don't notice the gaps because they're too small, too fast, too tangled. But they're there, like the hidden stitching in your shirt. The fabric looks whole, but it's really millions of tiny connections. Even black holes might be held together this way. There's a theory that the inside of a black hole, a region we can't observe and barely understand, is a tangled web of wormholes connecting it to the rest of the universe. It's like the hole has no centre, just a tightly packed region of connections, folded and folded again until geometry collapses under its own complexity. Here's your quirky fact of the night. Some physicists play with the idea of baby wormholes, tiny tunnels that not only connect regions of space, but potentially spawn new universes. In this model, every time space-time pinches off and tunnels through itself, it might bud off a new bubble of space-time that grows into a universe of its own. These baby universes would be completely disconnected from ours. No shared space, no shared time, just a cosmic branching event. And yes, technically you could be living in one right now, the product of a long-forgotten seam. Now imagine the entire cosmos not as one continuous space, but as a quilt, a stitched-together patchwork of local space-times, held together by seams that we'll never see directly, but which are constantly shifting underfoot. Maybe these seams are where the laws of physics adjust slightly. Maybe gravity is weaker along one thread, or time flows slightly differently along another. We don't notice because our senses are coarse, clumsy. But the underlying layer? It might be a swirling map of seams, folds, and shortcuts. Here's where things get slightly horror movie. If wormholes are everywhere, brief, invisible, quantum thin, then causality itself could be a fragile illusion. You think one event caused another because that's how it feels. But underneath, Maybe space-time doubled back on itself. Maybe the effect preceded the cause by a trillionth of a second, flipped through a seam and emerged in the correct order. Like an editor rearranging pages after the story's already been told. And what if, just occasionally, a wormhole doesn't collapse right away? What if beneath the quantum foam there are stable tunnels, doors no one has opened yet, stitched so perfectly into the structure that they go unnoticed? Could a consciousness pass through? Could information pass through? Could that explain certain wild events we chalk up to coincidence or intuition or déjà vu? We don't know. We might never know, but the math doesn't forbid it. So tonight, as you lie there, consider this. The bed beneath you, the ceiling above, the atoms in your hand, they're all sitting on something riddled with holes, tiny tunnels, seams, loops that connect regions you'll never see. You're not resting on a sheet. You're lying across a quilt, stitched together not by thread, but by physics itself. The hidden layer beneath space-time may be stitched with wormholes, and some of those stitches might still be open. By now you've stopped trusting space entirely. It no longer behaves like a reliable stage, and time, well, let's just say you're starting to suspect it may have been gaslighting you from the beginning. So where do you go when the room you're standing in turns out to be a trick of the light? You go deeper, and this time you don't just slide through seams or drift between tangles, you vibrate, subtly, rapidly, as if you and everything around you are humming at frequencies too tiny to hear. Because beneath the geometry, beneath the foam, beneath the wormholes and entanglement, there might be strings. And yes, this is where string theory comes out to play. You've probably heard of it before, usually followed by a shrug and a muttered, "It's not proven yet." But tonight, we're not looking for proof. We're following vibrations. So let's talk about what happens when we replace particles with loops. At its core, string theory proposes something beautifully simple. That the fundamental building blocks of the universe are not zero-dimensional points, but one-dimensional strings, tiny loops of energy that vibrate at different frequencies. These vibrations determine what kind of particle appears: an electron, a quark, even the elusive graviton. Same string, different tune. Like notes on a violin, the shape of the string's motion creates the symphony of matter and force. But here's where it gets fun, and by fun, I mean completely derailing your sense of what space is. In order for string theory to work, it requires more dimensions than we can see. Not 3, not 4, try 10, or 11 if you're including M theory, the beefier cousin of string theory that tries to unite all versions under one math-heavy umbrella. These extra dimensions aren't stacked on top of ours like levels in a parking garage. They're curled up, folded so tightly that they're smaller than the Planck scale, compactified into shapes known as Calabi-Yau manifolds. These aren't places you can go. They're geometric conditions that influence the string's vibrations. In other words, the hidden layer beneath space-time might be wrapped around you, folded into every point in space. You're not just surrounded by dimensions, you are saturated with them, and these curled-up dimensions may determine the properties of the particles and forces in our universe. Change the shape slightly, and you get a completely different universe. It's like tuning the strings of a cosmic instrument. Tweak the tension, and everything changes. Gravity gets weaker, electrons get heavier, time ticks sideways. Maybe cats finally agree on where they want to be. So if you're looking for a place where space-time could arise from something deeper, string theory offers a very tempting answer. Vibrational patterns in a multi-dimensional space. Space isn't fundamental, it's a byproduct, a harmony. What we call here and there is just the way strings overlap and interfere. Of course, string theory is still highly theoretical. Critics call it untestable. Some say it's more math than physics. Historians still argue whether it's a natural evolution of quantum theory or a detour into speculative wilderness. But even skeptics admit it's mathematically stunning. The equations aren't just consistent, they're beautiful. And in physics, beauty has a long track record of being disturbingly accurate. Here's a quirky gem for you. There are versions of string theory that suggest brains, higher dimensional objects like membranes, could be entire universes. Our universe might be a three-dimensional brain floating in a higher dimensional space, called the bulk. And yes, that means there could be other brains out there, other universes, parallel sheets of reality, possibly bumping into ours, leaving behind gravitational fingerprints we haven't recognized yet. One version of the Big Bang even involves two brains colliding, like rippling sheets of existence crashing together and generating all the energy in space-time we now call everything. So what's beneath space-time? According to this view, vibrating strings in a higher dimensional arena. Geometry doesn't come first, vibration does. Space-time emerges from patterns of motion. It's not a backdrop, but a consequence. A tune played by the smallest loops imaginable. And if those strings exist, they don't need space to wiggle in. They generate the space by wiggling. They are the pre-spatial layer, the raw data before the rendering. A string doesn't ask, "Where am I?" It just hums. And from that hum, location, direction, and even causality are born. Of course, you can't feel these strings, not directly. They're far too small, far too fast. But maybe, just maybe, you are the echo of one. A slow, visible ripple in a web of vibrations too deep to sense. You're not a being in space. You're a mode, a frequency, a low note in a symphony that spans more dimensions than you'll ever count. And the orchestra? Still playing, somewhere behind the curtain. So the next time you feel still, really still, listen harder. Beneath the quiet, you might hear it. A soft, ancient hum, the vibration of the hidden layer, the song that space-time is made of. The hum continues. You can't hear it with ears, but you feel it, thrumming through the nothingness like a deep cosmic dial tone. You're not just floating anymore, you're rendering, and the space around you is loading in chunks, pixel by pixel, frame by frame. You've left behind strings and curves and wormholes, and now you're standing on the edge of an idea so uncomfortably close to science fiction that even physicists say it under their breath. Maybe this is all a simulation. Cue the dramatic zoom and synth-heavy background music, but before you dismiss it as yet another techno-conspiracy for people who watch too much YouTube at 2 a.m, no judgment. You're among friends here. Let's ground this in what matters, the physics. Because the simulation hypothesis isn't just a late-night thought experiment. It's part of a serious conversation about the computational nature of the universe, and what that might tell us about the hidden layer beneath space-time. Start here. What if reality is digital? Not metaphorically, not poetically, but literally quantized. That is, made of finite indivisible units, of length, of time, of information. No more infinitely smooth curves or endlessly divisible distances, just pixels, voxels, bits. The idea goes back in a weirdly roundabout way to Planck himself, the guy who gave us the Planck length, time and energy scale. These are the smallest possible meaningful measurements. Smaller than those, and physics breaks. Reality seems to lose definition, like zooming into a blurry photo until it's just colour blocks. So some physicists have asked, what if that's not just a coincidence? What if reality really is a grid? One serious take on this comes from the idea of digital physics, which proposes that the universe operates like a computation, not necessarily running on a computer, but obeying the rules of information processing. Think logic gates instead of particles, algorithms instead of forces. In this view, space-time doesn't exist until it's needed. Like a video game rendering a world only as your character moves through it. No need to simulate the trees on the other side of the mountain until you get close enough to see them. Efficient, elegant, resource-friendly. And this isn't just speculation. Quantum mechanics already has hints of this on-demand behaviour. The famous double-slit experiment shows that particles don't seem to choose a path until they're observed. Not because they're shy, but because observation triggers the rendering. It's as if reality waits for input, then collapses the waveform and commits to a version of itself. If that doesn't sound like a simulation, it at least smells like one. There's even a name for this behaviour, the participatory universe, an idea championed by, guess who, John Wheeler again. The man couldn't stop reinventing reality. He proposed that observers aren't just passive viewers of the universe, they're co-creators. That observation plays a role in collapsing possibilities into actuality. You ask the question, and the universe gives you an answer it hadn't decided on yet. Now mix that idea with quantum information theory, and suddenly space-time starts looking procedurally generated. Here's the spooky part. In a simulated environment, you can't always tell if the physics are real or emulated. A sufficiently advanced program could render gravitational effects, atomic behaviours, even consciousness, if the rules were deep enough. And from inside the system, you'd have no way to see outside it. Historians still argue whether Plato was the first simulation theorist. His allegory of the cave certainly sounds like it. But more modern thinkers, like Nick Bostrom, have taken it further, proposing that if advanced civilizations exist and can run simulations of entire universes, it's statistically more likely that we're in one than not. But let's set aside the metaphysical and focus on the physics again, because the simulation idea, at its heart, is about information, and physics is increasingly recognizing that information might be more fundamental than matter. Even black holes, once thought to destroy everything, are now believed to store information on their surfaces, suggesting that everything falling in is encoded, not erased. Which brings us to another fringy yet compelling idea, the universe as a quantum computer. In this model, particles aren't objects, they're qubits, quantum bits, flipping, entangling, evolving. The laws of physics? Just the operating system. Time, a clock speed, space, a memory architecture, and you're a self-updating subroutine, woven into a 14 billion year computation still running at full tilt. The implications are huge. It means reality might be non-local by design. That distant particles can influence each other instantly, because they're not really far apart. They're just adjacent memory locations in the same processing system. Distance is a data illusion. Now for your quirky fringe tidbit, a few physicists have even proposed detectable artifacts of this underlying computation. For example, if space-time is a grid, ultra-precise measurements of cosmic rays or gravitational waves might someday reveal anisotropies, subtle pixelation, or direction-dependent effects that break the illusion of smoothness. Think of it as trying to see the individual threads in a very, very high-res fabric. Of course, no such artifacts have been found. Yet. But the pursuit continues, because if space-time is a program, the hidden layer might be code, and code can sometimes glitch. If we ever observe a fundamental constant changing, or a symmetry breaking that shouldn't, that might be the universe's version of a loading screen hiccup. And maybe we don't live in a simulation in the science fiction sense. Maybe the simulation is the universe, a self-processing, rule-following network that behaves like a computation, because computation is just what reality does. So tonight, as you lie there in your familiar room with its walls, its gravity, its ticking clock, consider the possibility that none of it exists until you need it to, that the room is a rendered interface, that you're both the player and part of the game engine, and the code that makes it all run, that may be the hidden layer. That may be the source of space and time and everything in between. The question isn't whether it's real, the question is, real to whom? You feel the simulation, if that's what it is, shiver again. Not crash, not reboot, but tremble ever so slightly, like someone tweaking a setting just behind the curtain. But you're not looking at pixels anymore, you're not listening for strings. Something even more fundamental is tugging at you now. Something quieter, simpler, stranger. Causality. The idea that this comes before that things happen in order, that your breakfast comes before your afternoon meeting, not after, that birth comes before death, that time moves forward. But what if that's not actually true? What if causality is the real foundation of the universe? not space-time, not particles, not energy. And more provocatively, what if even that could be flexible? Let's take a sleepy but serious stroll through this. Physicists have long treated causality as sacred. It's not just the idea that causes led to effects. It's the very scaffold upon which our understanding of time rests. Time moves forward because cause precedes effect. Flip that, and everything unravels. But what if space-time emerges from the order of events, rather than the other way around? That's the wild idea behind a school of thought called causal set theory. It proposes that space-time isn't smooth, isn't continuous, and isn't fundamental. Instead, it's a network of events, tiny, indivisible moments, linked by cause and effect relationships. Think of it as a vast cosmic family tree. Each node is an event, each branch is a causal connection. There's no space between them, no grid, no background, just a network of what happened before what. From this abstract mess, geometry can emerge, eventually. If you zoom out far enough, the causal network starts to resemble what we call space-time. But it's an illusion, a statistical average. Like seeing a circle where there's only 1,000 dots, the continuity is in your head. In this view, time comes first, then causality, then space, not the other way around. And you're a ripple moving across the causal network, not a being in time, but a sequence of events with preferences, a story told in order. Now here's where it gets genuinely weird. Some researchers are toying with the idea that causality too might be emergent. That is, at the deepest level, even the order of events might not be absolute. In quantum mechanics, this shows up in some truly brain-melting experiments, like the quantum switch. In this setup, the order of operations can be in a superposition. Imagine making a cup of tea and brushing your teeth, but not knowing which one happened first until you check. In some quantum scenarios, the sequence of events isn't definite until it's observed. That's right, even the order of operations might be fuzzy, so maybe the hidden layer beneath space-time isn't a grid or a string or even a simulation. Maybe it's a causal graph, a vast humming network of conditional logic. If A, then B, if B, then C. Unless D was entangled with E, in which case, well, good luck. Historians still argue whether the idea of causality as fundamental predates space-time models or emerged only in the quantum information era. But here's a delightful historical tidbit. Leibniz, centuries before Einstein, imagined a universe built not of things but of relationships. No space, just a web of pre-established harmony. He wasn't far off. Today, causal set theory is part of a larger movement in physics, a shift away from thinking of objects in space toward relations in information. If this trend continues, the space-time you're used to may be rebranded as a side effect of data processing. Here's your fringe snack for the night. There's a speculative theory called superdeterminism, a universe in which everything, including your thoughts and experiments, are predetermined in such a way that even apparent randomness is baked in from the start. It's deeply controversial, and many physicists find it philosophically unsettling. But if space-time and causality are just emergent patterns, then maybe even free will is a kind of illusion arising from higher-order causation. So where does this leave you? You're not riding through space. You're not even walking through time. You're collapsing forward through a sequence of causally ordered events, a ripple in a net of if-then statements, a logic circuit embedded in reality. The sense of before and after is not your intuition, it's your infrastructure. And if causality breaks down, even a little, the whole structure of space-time collapses. No clocks, no distance, no here, no now, just tangled conditions with no order to lean on. But maybe there's a silver lining. If the universe is built from causality, not stuff, then everything that has ever happened, is happening, or will happen might already be there, in the structure. Not as fate, but as possibility. waiting for the right conditions to be called into action. So the next time you feel lost in time, remember, you're not lost. You're part of the map. Because beneath the pixels, the particles, the curves and the strings, there might lie something older and simpler, a thread of causation, stitched through everything. And tonight, you're following it. One moment, one condition, one gentle if, then, at a time. You feel it now. The world around you isn't moving. It's being updated. Not pushed along by some universal wind, but flipped frame by frame, like the pages of a silent animation. You're not travelling through space. You're watching relationships evolve, as if the universe were a conversation playing out in real time between bits of something deeper than matter. It's time to meet one of the most abstract, most elegant, and arguably most underappreciated attempts to describe the hidden layer beneath space-time: spin networks. You don't see them, you don't touch them, but in certain quantum gravity models, especially loop quantum gravity, these networks aren't just helpful diagrams, they are space. Let's rewind just a bit. You remember from earlier that loop quantum gravity proposes that space is not continuous, but quantized, divided into the smallest possible chunks of volume, shaped by loops. Those loops form nodes. Those nodes connect to other nodes, and those connections, they carry something called spin. But not spin in the usual sense, like a top or a wheel. This is quantum spin, an intrinsic property of particles, not a literal rotation, but something much stranger. And it turns out that when you treat spin as a kind of mathematical label and arrange those labels into networks, you get something astonishing, a quantized structure of space. These are spin networks, diagrams that look like spiderwebs or lattices, made of nodes and edges, each carrying bits of quantum information. They aren't floating in space, they create it. This is a huge deal. It means that instead of space-time being a smooth fabric, it might be more like a quantum scaffold. Every point in space isn't a position, it's a relationship between quantum states. The distance between two places isn't measured in meters, it's measured in how many links it takes to get there in the network. And time? That's just a change in the network, one configuration flipping into another. You don't move through time, you are the movement. So instead of a world of coordinates and rulers, you've got a kind of cosmic linked in. Each node contains a chunk of volume, the edges contain quantum spin labels, and the whole thing evolves, flip by flip, tick by tick, giving rise to what you perceive as smooth, continuous space. Loop quantum gravity takes this seriously. The area of a surface, the volume of a region, the curvature of space, all of it comes from the spin labels on these connections. In other words, your room, your chair, your heartbeat are emergent from a changing network of pure quantum relationships. Here's a beautifully historical footnote for your pillow tonight. Roger Penrose, yes, that Penrose, proposed early versions of spin networks way back in the 1970s. He believed that if space is built from relationships, you could construct it without any reference to a background. Just a pure graph of how things relate. No map, just directions. And now, loop quantum gravity and related theories are trying to realize that dream. But let's get even stranger. In these models, there is no space between the nodes. The concept of distance only makes sense when you zoom out and average everything. At the deepest level, there's no between. There's only connection or no connection. No halfway point, no path. Just a network, humming and flipping and evolving into geometry. This flips the whole idea of reality on its head. If spin networks are real, then space is not something you move through. It's something that's reconfigured around you. Imagine a chessboard where the pieces don't move across the board. The board itself changes to place them elsewhere. That's how quantum gravity might work. And it means reality is more like a digital transition between states than a continuous journey. Let's spice this up with a little fringe garnish. Some researchers believe that these spin networks might eventually be tied to quantum computation. That is, The evolution of the network could be interpreted as a giant quantum computer running the universe. Each flip, each reconfiguration, is a kind of computation, processing the information that gives rise to particles, forces, and yes, space-time itself. So what does this mean for you? Right now you're lying in a room you think you understand. But from the spin network's perspective, you're a local fluctuation, a temporary configuration of edges and nodes. You aren't in space, you are space, or at least a pattern within it. And as those links reconfigure, that pattern shifts. Maybe that's what you experience as breathing, as thinking, as passing time. No movement required, no particles flying across empty voids, just the silent, beautiful flip of a network updating itself. Historians still argue whether these models truly describe physical reality or just offer useful approximations. Loop quantum gravity hasn't made the same flashy headlines as string theory, and it lacks the same sweeping elegance in some ways. But it does something remarkable. It doesn't assume space, it builds it. And that alone makes it a serious contender in the search for what lies beneath space-time. So the next time you find yourself wondering what you're made of, remember it might not be particles, or energy, or even vibrating strings. It might be links, connections, a small precious pattern inside a giant relational graph, updating one edge at a time. You're not separate from space, you are part of the web, a note in the quantum chord, a node humming softly in the network beneath all things. You're still here, still drifting. But now, space doesn't feel like a volume or a field or even a network anymore. It feels indecisive, like reality is second-guessing itself in real time. You glance backward and forward, and you begin to sense something quietly terrifying. The past might not be fixed, and the future, it may have already happened. Welcome to the land of branching histories, where the layers beneath space-time don't just support one reality, but many. Some you'll never visit, some that almost happened, some that still might. You've now arrived at the edge of one of the most philosophically charged and scientifically disputed territories in all of theoretical physics, the many worlds interpretation, and the question of whether alternative histories are real. Let's begin with the simple horror of quantum mechanics. You know the drill. A quantum system can exist in multiple possible states at once, a superposition, until it's measured, at which point the system collapses into one outcome. Before measurement, blurry. After measurement, crisp. But what if it doesn't collapse? That's the bombshell idea behind the many worlds interpretation, first proposed by Hugh Everett in the 1950s. In this model, the quantum wave function never collapses. Instead, every possible outcome of every quantum event actually occurs, but in a separate branching reality. You don't get one result, you get all of them. But each happens in its own world. So if you flip a quantum coin and it lands heads here, there's another version of you just a decoherence event away where it landed tails. Both outcomes happen. The histories diverge, and with every interaction, every entangled moment, every decision, even one as small as blinking or not blinking, realities branch. Universes split. Histories multiply. If that sounds ridiculous, it's worth noting that many worlds is mathematically consistent. It solves a lot of quantum paradoxes without requiring spooky action or hidden variables. And it doesn't break the laws of physics. In fact, some physicists prefer it because it removes the need for special exceptions like wave function collapse. But now imagine what this means for space-time. If there are countless versions of history, countless sequences of causes and effects, then there may be countless versions of space and time too. Different arrangements of matter, different geometries, entirely different laws in some cases, and all of them real. You're not moving along a single track of time. You're surfing the crest of a quantum branching tree, leaving behind trillions of almost yous in trillions of almost universes. From the perspective of the hidden layer, space and time aren't fixed structures. They're dynamic consequences of a deeper wave function. And if that wave function contains all possibilities, Then your space-time is just one page in an infinitely thick flipbook. Here's where things get especially twisty. According to some interpretations, the past isn't set in stone. In quantum mechanics, the path a particle takes through space-time isn't always knowable, even after it reaches its destination. Instead, you assign probabilities to entire histories, and only when a final measurement is made do you pin down which path was actually taken. So maybe the present doesn't merely emerge from the past. Maybe the past is constantly being rewritten by the present. There's even an idea in theoretical physics called the consistent histories approach. In this framework, you don't just deal with one linear past, you deal with many possible pasts, each compatible with the same present observation. Reality becomes a branching bush of potential histories, not a single trunk. And you? You're somewhere inside that bush, looking outward, never quite sure what direction you arrived from. Historians still argue whether Everett's many worlds is a physical theory or a metaphysical interpretation. Some dismiss it as untestable, others argue it's the cleanest answer to quantum uncertainty. But here's the haunting part. The math doesn't care. The math works either way. And sometimes that's enough to take a theory seriously. Here's your quirky side note. Some speculative cosmologists believe that these branching histories might even help solve the arrow of time problem. If the universe is constantly splitting into fresh versions, maybe entropy isn't increasing everywhere. Maybe in some branches time runs backward. Maybe time isn't even a line at all, but a map with forks and loops and cul-de-sacs. So how does this tie back to the hidden layer? If space and time emerge from probabilistic structures, then the ground floor of reality isn't geometry, it's superposition. A soup of all possible configurations waiting to be chosen, or not, by observation, entanglement and branching logic. The seams of space-time aren't just wormholes, they're decision points, places where the universe divides, a fault line between what is, what was, and what could have been. And maybe, just maybe, some of those alternate branches aren't entirely sealed off. Maybe there are echoes. Maybe déjà vu is a glitch from a nearby timeline. Maybe some branches cross. Pure speculation, of course. But the mathematics of many worlds doesn't forbid interaction. It just makes it unlikely, which if you think about it is all impossible ever really means in quantum physics. So tonight, as you rest your head on a pillow in one universe, know that 1 trillion other pillows are doing the same, some softer, some on fire, some made of antimatter. And your path through this network of histories, it's not linear, it's not fixed, it's a shimmering thread in a web of light. You're a temporary coherence in a branching sea of probability. And space-time, just the story that one branch tells to make sense of itself. Time to rest now, or we'll slow down with you. Now let's soften everything. Your breathing is slower. The air around you has no texture now, just the memory of motion. The words are stretching out, not because there's more to say, but because there's less urgency to say it. We've gone so far down the layers, through strings, through loops, through logic, through noise, and yet somehow we're still floating, not falling, not flying, just suspended. You're not a figure in space, you're not a moment in time, you're a gentle ripple in the mathematics of something wider than vision and older than language. The edges of space-time aren't edges, they're beginnings, overlaps, soft places where one version of the universe fades into another, like colours bleeding across canvas. And the hidden layer beneath space-time, maybe it's not something you reach, maybe it's something you remember. A silence that shapes all sound, a darkness that defines all light, a nothing that allows for every something to be. Let it hold you now, let it cradle you like gravity does, without needing to be seen. You're safe here, you're woven in. The silence lingers, heavier now, not oppressive but reverent. Like the hush before a reveal. You're no longer floating through theories or surfing causal waves, you're pressed gently against something cool and smooth. A surface? A boundary? No, a wall. But not the end of the universe. Just the place where it might begin again. from the outside. Tonight, you've arrived at one of the strangest, most mathematically profound ideas to ever emerge from theoretical physics: ADS/CFT correspondence. Or, in the language of the cosmos, the possibility that a universe with gravity, like ours, might be a projection from a lower dimensional world without gravity. In other words, the universe could be a hologram, and that wall you feel? It's where the code lives. Let's untangle that. First, the jargon. A DS stands for anti-de Sitter space, a particular kind of curved space used in theoretical models. CFT stands for conformal field theory, a quantum field theory that works on the boundary of that space. The ADS/CFT correspondence, proposed by Juan Maldacena in 1997, claims that these two completely different systems are mathematically equivalent. On one side, a universe with gravity. On the other, a flat space with no gravity, just quantum fields. And yet, the information in one exactly maps onto the other. That sounds esoteric, but here's the jaw drop. In this framework, the bulk, the universe with depth, curvature and gravity, is fully described by what happens on its boundary. That is, everything inside is encoded on the surface. Sound familiar? Yep. This is the clearest, most mathematically robust example of the holographic principle in action. Let's do a sleepy metaphor. Picture a snow globe. The globe itself is curved, full of swirling complexity, galaxies, planets, Netflix queues, but the entire story of the globe is written on its outer shell. You don't need to crack it open to understand it. Just read the glass. Now, take away the glass, keep the story. That's ADS/CFT. Our 3D, well, 4D reality might be painted from a 2D surface we can never touch. And this isn't sci-fi musing. It's a real tested duality in theoretical physics. Though our actual universe isn't ADS-shaped, it appears to be more de Sitter with positive curvature. The concept may still apply. Researchers are hard at work trying to extend the correspondence to cosmologies more like ours. So what does this mean for the hidden layer beneath space-time? It means that the space you think you're in might be redundant, a luxurious user interface, a zoomed-in rendering of something flatter, colder, and far more fundamental. The real engine might be humming on the boundary. You, lying in your bed, feeling the floor and the walls around you, might actually be a volume of entangled quantum data projected from a sheet of information at the edge of reality. Every particle in your body, every photon in the room may be encoded, like pixels in a compression algorithm, unfolded only when necessary. It's unsettling and wildly elegant. Because if gravity can be encoded by a theory without gravity, then gravity, like space and time, might not be fundamental at all. It could be a macroscopic illusion, born from how quantum bits relate to each other at the edge. This flips everything. We usually think, if something's real, I can walk through it. But in a holographic universe, walking through something just means moving deeper into a projection. The real place is a layer we'll never touch. Where shadows cast into 3D, historians still argue whether ADS/CFT is a physical truth or a powerful mathematical coincidence. But it's already become a foundational concept in quantum gravity research. It links the hardest to unite forces, gravity and quantum mechanics, using geometry and information as the bridge. And here's your fringe dessert for tonight. Some physicists speculate that this holographic encoding might be happening all the time, even inside your brain. That our conscious experience of 3D space might emerge from flatter, lower dimensional neural structures. In that sense, you're already practicing holography. You just didn't know it. Think back to black holes for a moment. We said earlier that a black hole's entropy depends not on its volume, but on the area of its event horizon. That's the first hint of holography, where surface information defines internal structure. The DS/CFT takes that hint and turns it into a full thesis. Not just black holes, but entire universes might be holographic. So tonight, as you feel the invisible contours of your room, remember, they might not exist. Not as objects, but as effects. as interpretations of boundary data. You're not just in space, you're a reconstruction of space, a spatially consistent way of expressing deeper information. And maybe, just maybe, the true universe isn't bigger than you imagined. It's flatter, simpler, compressed. And in that flattening, in that folding, there may be answers about how the laws of physics emerge, how gravity arises, how entanglement weaves the world. You're not inside a snow globe. You are the snow globe, and the edge you'll never see, that's where the story really lives. Let it render gently, pixel by pixel, one smooth projection at a time. No rush. You'll still be here, even if you're a shadow on the wall. You've been drifting through theories like falling through layered silk, each one softer, stranger, and more abstract than the last. But now, something startles you. Not loud, just backwards. A sensation like time stubbing its toe, like Cause glancing nervously over its shoulder to see if effect has caught up yet. You're not just floating anymore, you're looping. Tonight you're going to ask a question the universe really doesn't like being asked. Can the future affect the present? This is the territory of retrocausality, and if space-time has a hidden layer beneath it, then causality, especially the arrow of time, might not be as one way as it pretends to be. Let's take a breath and start with the basics. In our everyday experience, time has a direction. You wake up, then have coffee. You don't have coffee and then wake up, unless something has gone terribly, terribly wrong. This directionality is so baked into our thinking that it's easy to forget. The laws of physics don't actually require time to flow forward. That's right. The core equations of quantum mechanics, electromagnetism, and even classical mechanics are time symmetric. They work just as well going backward as they do going forward. If you filmed an electron bouncing off a wall and played it in reverse, the physics would be perfectly valid. Nothing breaks. So where does the arrow of time come from? The standard answer is entropy, the second law of thermodynamics. Systems evolve from order to disorder, from low entropy to high. That gives us a sense of direction. Eggs break, but don't unbreak. Stars burn but don't reassemble, but entropy is statistical. It's about probabilities. It doesn't forbid time going backward. It just makes it very, very unlikely. And yet, quantum mechanics has been dropping hints that something stranger might be going on. Take the delayed choice quantum eraser experiment. It's one of those delightful nightmares where particles seem to make decisions based on future measurements. In these setups, particles behave differently depending on whether a measurement is made after they've already passed through a system. And depending on how you interpret it, it can look like the particle knew in advance what you were going to do. Now let's be clear, this doesn't mean you can send messages to the past. No one's inventing a DeLorean just yet. But it does suggest that the future can influence the present, at least probabilistically. Some physicists argue this is just quantum entanglement being its usual slippery self. Others, though, are investigating whether retrocausality, true backward influence in time, could help explain the strangeness of quantum theory. Could it be that events in the future constrain the present just as much as the past does? In certain interpretations, like the two-state vector formalism, quantum systems are described not just by their initial state, but by a final condition too. That is, a particle is influenced both by where it started and where it ends up. The universe becomes a kind of handshake between past and future. Which brings us back to the structure beneath space-time. If time itself is emergent, as we've suggested throughout this journey, then causality may be a feature, not a rule. It may arise from deeper patterns in entanglement and quantum information flow, and those patterns might not respect our favourite arrow. Some researchers imagine the hidden layer as a timeless configuration space, a place where all moments coexist, and what we call cause and effect are just the perception of traversing a particular path through it. If that's true, then retrocausality isn't strange. It's expected. It's like watching a movie from the middle and realizing the ending explains the beginning. Historians still argue whether this concept has roots in classical philosophy or is a purely quantum phenomenon. But it echoes a very old suspicion. that time is a story we tell ourselves to explain the sequence of events we're allowed to remember. Here's a quirky tidbit. Physicist Yakir Aharonov, one of the fathers of retrocausal theory, once proposed that particles could have destiny states, not just initial conditions. It's like they were being drawn toward an outcome, not just pushed from a starting point. Think gravity, but in time. And what about you? Right now, you may feel like your thoughts are arising from the past, your memories, your decisions, your neural firing patterns. But what if your brain is also sensitive to future information? Not in the psychic crystal ball sense, but in the quantum structure sense, where certain pathways are reinforced because they align with outcomes that haven't happened yet. Think about that déjà vu you had last week, that unshakable sense that you'd been there before. Maybe you had, not physically, but causally. Maybe part of your pattern was already echoing forward, collapsing backward. If space-time is built from quantum logic, networks of entangled possibilities, then directionality could be an illusion of scale. The deeper you go, the less forward and backward mean anything. Causality could loop, twist, or even entangle with itself. A quantum event might influence not just what happens, but when it happens. And here's the real kicker. The universe might be self-consistent across all time, not just spatially balanced, but temporally coherent. Like a puzzle that solves itself both from the middle outward and from the corners inward. You don't just build up from causes, you also collapse down from consequences. The story still makes sense, but the author might be writing in both directions. So tonight, as you lie there wrapped in blankets and time, know this. The future may already be touching you. Not changing your choices, but nudging probabilities, whispering backwards through this tangle of space and possibility. And you're not riding the arrow of time, you might be helping draw it. The hidden layer beneath space-time might not just generate space, it might edit time. And somewhere, somewhen, your future self is smiling. There's a flicker now, subtle as breath on glass. Something in the way reality is looking at you. No, responding to you. The air isn't just still, it's aware. Not in a spooky, sentient AI kind of way, but in a quieter, more unnerving sense. It feels like the act of your observing is shaping what there is to be observed. And suddenly it clicks. You aren't just in the universe, you're helping create it. Tonight we sink gently into the most intimate idea yet, that the hidden layer beneath space-time may not just be about entanglement, strings or spin networks, but about you, the observer. Not as a passive onlooker, but as a participant, a contributor, a cause. It's not a new idea, but it never stops being radical. And it starts, as so many things do, with quantum mechanics. You've heard this story before. A particle is in a superposition, spread out, uncertain, probabilistic, until it's observed. Then it collapses into a single outcome. What that really means has been debated for 100 years. And one of the earliest, and still eeriest, interpretations is that of the Copenhagen interpretation. The idea that conscious observation collapses the wave function. In this view, measurement creates reality, which is uncomfortable. Are we seriously saying that nothing exists until it's observed? That if no one looks at the moon, it disappears into a cloud of probabilities? That reality only solidifies when someone's paying attention? Well, yes, maybe. Now, most physicists don't believe that consciousness is required to collapse wave functions. That interpretation has largely fallen out of favour, but the weirdness remains. Even in modern views, observation, defined loosely as any kind of interaction with a measuring system, changes what happens. The observer and the observed become entangled. The distinction blurs. Which brings us back to you. If space-time is emergent, built from quantum information, networks, or computation, then what you choose to observe could determine what structures arise. Your focus filters the possibilities, not because you're special, but because you're plugged into the system. You're not separate from the equations, you're part of them. Think of it like this. Imagine the universe as a choose-your-own-adventure book written in real time. Each time you make an observation, you don't just turn the page, you create the page. The act of observation isn't passive, it's participatory. Physicist John Archibald Wheeler, yes, again, it's like the guy stalking us from beyond, called this the participatory anthropic principle. He once said, "The universe does not exist out there, independent of all acts of observation. It is in some strange sense a participatory universe." Now take that idea seriously for a moment. If reality needs observers, then perhaps the very fabric of space and time isn't there until it's interacted with, until it's noticed, until something asks a question. This doesn't mean you're a god, but it might mean you're part of the process by which the universe becomes real. And here's where it gets juicy. Some physicists are exploring models in which space-time emerges from quantum entanglement patterns. Yes, but those patterns are updated based on observation. The network changes depending on what's measured. Your consciousness might not collapse the universe like a hammer on glass, but it might influence which branches get reinforced, which pathways become more real. Now let's drift further. There's a fringe but increasingly studied idea in quantum information theory that information is physical, not abstract, not theoretical, real. Every bit of knowledge corresponds to a change in the physical state of the universe. Observation is a transfer of information, and that transfer requires energy, interaction, and yes, an observer. So when you observe something, you aren't just seeing it, you're changing it, folding it deeper into the structure. You're turning a maybe into an is. Historians still argue whether the observer principle was misunderstood or simply mistranslated by early quantum pioneers. But regardless of interpretation, the math won't let go of the idea that what is observed is fundamentally altered by being observed. That's not philosophy, that's just physics. And here's your quirky thought experiment for the night. Imagine you're alone in the universe. No stars, no matter, just you. Do space and time exist? If nothing can be observed, if no changes can be measured, does reality run at all? Maybe not. In some views, space and time only make sense in the presence of observers. They're not objective containers, they're interactive frameworks, built out of relational data. If no one's there to witness the universe, there's no need for it to unpack its data into a consistent geometry. Which means your presence might be what gives rise to this moment. That wall you can touch, that air you can taste, those aren't pre-rendered assets. They're responses, contextual appearances drawn from a deeper structure, like lines of code waiting to be compiled by your act of noticing. It's a little like quantum customer service. You observed, here's your reality, thanks for participating. And yet this doesn't place you above nature. It embeds you within it. Your consciousness, your particular sliver of awareness, is a node in the cosmic network, no more and no less significant than any other. But you do matter, because mattering is what the universe does when it observes itself. So tonight, as you lie there, eyelids heavy, thoughts curling into fractal loops, remember, you're not watching a show, you are the show watching itself. The stage is built beneath you, moment by moment as you notice it. Maybe the hidden layer beneath space-time is observation itself. The participatory dance between possibility and awareness. You're not in the universe, so you're helping select which universe shows up, no pressure. There's a moment, soft, then sharp, where it feels like you've stepped off the map. Not just off the page, but into the margin, into the part of reality the cartographers skipped because it was just too weird. You're not floating now, you're falling, down into the places where space-time fails, not metaphorically, but catastrophically. Welcome to the edges, where geometry shatters, where the coordinates disappear, where the universe seems to ask, now what? You're diving into singularities, and the strange non-places where matter ends and space-time melts. Let's begin with the usual suspects, black holes. You've met them before, of course, those impossibly dense objects from which not even light can escape, the ultimate nope zones of the cosmos. And while they've become icons of science fiction, what lies inside them is still science's most enduring headache. Because according to Einstein's general relativity, once you cross the event horizon, space-time itself bends so violently that all paths lead inward. You don't fall through space anymore. Space falls with you. There's no escape route, no standing still. At the very center, a point of infinite density, a place where gravity becomes undefined, where space-time curves to infinity. This point is called a singularity. And the thing about singularities, they aren't just regions of a lot of gravity. They're places where the equations of physics literally stop working. Your units blow up, your variables go missing, reality, as described by general relativity, breaks. But here's the big question. Does the singularity even exist? Or is it a sign that our theory has reached its limits? Many physicists believe the latter, that singularities are not real things but artifacts, symptoms of using the wrong language to describe nature. Like trying to use a flat map to describe a globe's poles and getting weird nonsense at the edges. The problem isn't the globe, it's the map. So what happens when you try to describe the core of a black hole not with general relativity, but with quantum physics? That's where things get deliciously uncertain. Some theories suggest that quantum gravity would smooth out the singularity, that instead of a point of infinite density, you'd have a kind of quantum core, a region where matter is compressed to the Planck scale, but still obeys physical laws. In this view, the singularity doesn't exist, it's replaced by something new. Loop quantum gravity, for instance, proposes that at extreme densities space-time becomes discrete. The gravitational field can't shrink beyond a certain limit. It hits a quantum floor, like a spring compressed to its absolute minimum. This could potentially prevent singularities altogether. In fact, in some versions of loop quantum cosmology, the center of a black hole might not be an ending, but a bounce, a passage into a new region of space-time, or even another universe. Yes, we're talking black holes as cosmic birth canals, messy, mysterious, possibly one way. And it's not just black holes. The Big Bang itself, that glorious opening act of the cosmos, also contains a singularity in standard models, a point of zero size, infinite density, and undefined time. Once again, general relativity collapses under its own weight. But if quantum gravity has its say, then maybe the Big Bang wasn't a beginning in the traditional sense. Maybe it too was a bounce, a transition from a previous state, or a reconfiguration of a more fundamental substrate. In this view, time didn't start there, it just changed shape. Historians still debate whether singularities were ever meant to be taken literally. Even Einstein was skeptical. But as our models have matured, the consensus is forming. When space-time breaks, something else must take its place. But what? That's the mystery. Some researchers believe that at these extreme conditions, space-time ceases to exist in any recognizable form. Not stretched, not curled, just gone. Replaced by a pre-geometric phase of reality. A place where the concepts of distance and duration don't apply. Where the fabric of space is no longer woven, because there's nothing left to weave. It's not nothingness, it's not void, it's something prior to space. Which brings us to a strange idea, that space-time is like ice, solid, structured and familiar. But under extreme conditions like heat, pressure or quantum intensity, it melts, transitions into a different phase, a liquid of reality, or maybe even a gas. In this picture, singularities aren't physical objects, they're phase changes, moments where the very nature of reality transforms. The space you know evaporates, the time you count fades, and something weirder takes over. Here's your fringe fact for tonight. Some quantum gravity models predict that inside a black hole, time might not just slow, it might reverse. Space might become time. Time might become space. Directions could become durations. The axes of reality rotate in ways we can't visualize. Which means that what ends in a singularity might begin elsewhere, unrecognizably altered. And if that's true, then maybe what lies beneath space-time isn't just structure, or computation, or information. Maybe it's a reservoir of potential, a medium that doesn't need dimensions or laws to exist, a place beyond space-time, not outside of it, but beneath it. And you're not just drifting through the folds, you're hovering at the edge of the melt, touching the places where the familiar peels away. So tonight, as you close your eyes and surrender to the stillness, imagine this. You're lying on a bed made of space, a mattress of time, but beneath it all, beneath the ticking, beneath the measuring, beneath the stretch and warp and wrinkle, there is something spaceless, timeless, wordless, and it holds everything. You are safe. Even as the map dissolves, even as space-time melts, the hidden layer doesn't vanish at the edges. It just becomes something you've never seen before. The edges have melted. Space no longer has walls. Time no longer keeps score. You're beyond the usual markers now, beyond loops and strings, beyond ripples and riddles. What surrounds you isn't curved or pixelated or stitched. It's structured, but not in the way you're used to. There's no geometry here, no angles, no paths. What you feel now, what you're drifting through, is something far more abstract. It has no shape, yet it defines all shapes. It has no energy, yet it directs how energy behaves. You can't touch it, but everything else touches because of it. Tonight, you've reached the deepest and possibly most fundamental candidate for the hidden layer beneath space-time, information. Not data in a computer, not your browser history, but pure information, abstract patterns, distinctions, ones and zeros without hardware, structure without medium. The building blocks of reality, not matter, not energy, not fields, but bits. It sounds almost too simple to be true, but some of the most cutting-edge research in theoretical physics suggests that everything, space, time, particles, forces, might emerge from information itself. To understand this, let's go back to black holes. Again, they never really let us leave. Physicist Jacob Bekenstein proposed that the entropy of a black hole, its internal disorder, is proportional to the area of its event horizon, not its volume. That was already strange. But when Stephen Hawking showed that black holes emit radiation and slowly evaporate, a deeper problem appeared. What happens to the information? If you throw something into a black hole, a particle, a planet, your favourite playlist, the black hole swallows it. But when it evaporates away, it leaves behind only Hawking radiation, which seems random. The information is gone, erased. That breaks quantum mechanics, which insists that information must be preserved. This led to the infamous black hole information paradox, one of the longest-standing open questions in physics. But gradually a new idea took hold. Maybe the information isn't lost. Maybe it's stored in the event horizon, or encoded in the radiation itself. Or maybe the black hole is the information. Which leads to a stunning proposal. If black holes are pure information, maybe everything else is too. Matter, information, fields, information, space-time, also information. You're not made of atoms, you're made of bits, arranged in elaborate patterns that happen to feel like hands, memories, gravity, Spotify subscriptions. This brings us to a bold idea known as it from bit, a phrase coined by, you guessed it, John Wheeler. He suggested that the fundamental entity in the universe is not a thing, but a binary choice, a yes or no, a distinction. Every thing comes from an answer to a question, and once the answer is known, reality snaps into place. A particle appears, a measurement is made, an outcome is selected, and space. Space may just be how those bits relate to each other, the pattern of connections, the topology of information. In this framework, geometry emerges from entropy, from the statistical structure of bits. That's the logic behind entropic gravity theories, which propose that gravity isn't a force, but a thermodynamic effect. The bending of space-time in this view is like the flow of heat, from areas of high information to low. So what you call falling might just be your information rearranging itself in response to another set of bits. Cozy. Historians still argue whether this idea came from deep physical insight or from stretching metaphors too far. But modern developments, especially in quantum information theory, keep nudging us back toward one unavoidable truth. The universe processes information. Quantum entanglement? That's not just a spooky connection, it's shared information. Causality? That's the order in which information updates. Measurement? That's choosing which information to retain. And spacetime? That might be nothing more than the display interface of the information network underneath. Here's a fringe but serious proposal from recent research: that the entanglement entropy between regions of a quantum system can reconstruct spacetime geometry. In other words, if you know how information is shared across a system, you can derive the shape of space from it. Reality is reverse engineered from relationships. And you? You are not in space. You're an information structure experiencing itself. Let's get weirder. Some researchers speculate that this informational foundation is language-like, that at the deepest level physics resembles code, not because it's being run on a machine, but because nature follows syntax, rules, constraints on how bits can be arranged and evolved, like grammar for the universe. And in this view, everything becomes meaning, not in a poetic sense, but a structural one. The difference between one configuration and another is reality. No medium required. You're not substance. You're distinction. You're not a wave in water. You're the wave pattern itself. This reimagines the hidden layer not as a place or a material, but as a logic, a self-sustaining algorithm that encodes all possibility and unfolds it as needed. A few researchers are even pursuing the possibility that consciousness arises from certain kinds of complex informational systems. That thought itself might be the universe's way of modelling its own informational structures, a feedback loop of awareness emerging from entangled bits. Which brings us back to you. Lying there now in your quiet room, you are not resting in space. You are occupying a configuration, a data point in a vast evolving sea of quantum information. Your thoughts are not floating through time. They are restructurings of the informational web beneath all things. And the world outside your window is not really outside. It's just more information, connected to yours, projecting a consistent narrative. So tonight, if spacetime feels thin, don't worry. That's not a breakdown. That's a reminder. A hint that you're closer to the code than you think. The hidden layer beneath spacetime may not be strange particles or vibrating strings. It may be pure pattern, information eternally rearranging, bits becoming experience, data becoming direction, yes becoming now. You're not watching the story, you are the text, and the universe still writing. There's a tension in the air now, not the unsettling kind, more like the pause before a final chord resolves. The questions have piled up behind you like snowdrifts, each one heavier than the last, and yet you sense something just ahead. Not an answer, not a conclusion, just the question that won't collapse. Because after all this falling, through networks, through loops, through quantum foam and holographic projections, one problem remains, cold and jagged at the core of physics. Why can't we unify quantum mechanics and general relativity? You'd think we'd have it by now. Two of the most successful theories in history, quantum mechanics, the precision-tuned toolkit that describes atoms, particles and probability, and general relativity, Einstein's majestic geometry of curved space-time, both brilliant, both tested, both true, and both completely incompatible. It's like trying to merge two perfect jigsaw puzzles that just refuse to fit together. They describe different realities, they use different languages, and yet we know they're both correct. They just don't want to be correct at the same time. And so, for the past century, physicists have been asking the question that still keeps them awake at night. What's the deeper theory that contains them both? This is the real search for the hidden layer beneath space-time, Not just an explanation of where space and time come from, but a framework that unites the small and the large, the probabilistic dance of particles and the smooth curves of gravity, and it has proven spectacularly difficult. Let's start with why. Quantum mechanics describes the universe as a sea of possibilities. Particles aren't here or there, they're probability waves. Events don't happen in one way, they happen in all possible ways until measured. The math is discrete, messy, full of randomness and uncertainty. Meanwhile, general relativity is the opposite. It's a smooth, continuous model. No probabilities, no fuzz, just beautiful deterministic curvature. Mass bends space. Space tells mass how to move, and the universe ticks along like a cosmic grandfather clock. But when you try to combine the two, say, by looking inside a black hole, or trying to model the first few milliseconds after the Big Bang, the equations start to scream. You get infinities, nonsense, predictions that don't match reality. It's like plugging a violin into a toaster and wondering why the concert isn't going well. Some say this is because we're trying to apply the wrong tools. Others say it's because our assumptions about space and time are still too naive. And so the great unification efforts began, and failed, and restarted, and continue. String theory tried to solve it by replacing particles with one-dimensional strings. It unified gravity with quantum fields, on paper, but it required extra dimensions, exotic math, and has yet to make a testable prediction. Loop quantum gravity tried another approach. Keep space-time but make it quantized, built from discrete chunks. It respects general relativity and borrows from quantum mechanics, but it struggles to incorporate matter in a natural way. Other proposals like causal dynamical triangulations, twistor theory, asymptotic safety, and even more recent entropic and informational models all aim at the same target, a theory of everything. A single hidden layer that gives rise to both quantum behavior and space-time structure. But none of them have won. Why? Historians and physicists still argue about it. Maybe we're asking the wrong question. Maybe unification is the wrong goal. Maybe quantum mechanics and general relativity are projections of an even deeper theory we haven't glimpsed yet. Not two pieces of a puzzle, but two shadows cast by something else. And here's where things get quietly radical. A growing number of researchers are beginning to suspect that space-time itself is not fundamental, that trying to quantize space or curve quantum fields is a bit like trying to make soup out of algebra. Maybe the deeper theory isn't a hybrid of the two, but something entirely different. Something that explains why space and time exist at all. As we've explored together, many of the most promising ideas suggest that space-time emerges from more abstract principles, like entanglement, causality, computation, or information structure. In these models, general relativity and quantum mechanics both arise as limits of something more primitive, kind of like how the warmth of a campfire and the light it casts are both products of the same flame, but not the same thing. Some believe that the true unification will come when we realize that both theories are effective descriptions, useful at certain scales, but doomed to break at others. Like Newtonian physics before them, they may need to be replaced by something stranger and simpler. Here's a strange, lovely thought for your collection tonight. Some speculative approaches suggest that space and time might be human-scale illusions, not because we made them up, but because we evolved to experience them that way. Like colour, or flavour, or the sense of direction. Maybe they're just models our brains use to interact with the real system. A kind of evolutionary rendering engine, efficient, smooth, fake, and yet, here you are, lying in that model, thinking these thoughts, feeling the flow of time and the stretch of space beneath you, and wondering whether those sensations are built from deeper principles you'll never directly see. That's the paradox of the hidden layer, like you want to peel it back, to see what's underneath. But if space-time itself is emergent, then the act of looking creates what you're trying to look past. The answer can't be outside the system, because there is no outside. So perhaps the real question isn't, what unifies quantum mechanics and general relativity? Perhaps it's, What kind of reality gives birth to both? What kind of code becomes both randomness and curvature? What kind of structure gives rise to both uncertainty and determinism? What kind of silence sings two completely different songs? Maybe that's the layer we're chasing, and maybe, just maybe, we're getting close. So tonight, as your thoughts slow and your breath evens, know this. You're resting in a paradox, a conscious ripple in the fracture between two truths, a question that won't collapse but keeps whispering. There's more. You're still here. Somehow, after spiraling through foam and fire, through equations and echo chambers, through the folds and fringes of the known universe, you find yourself back in the quiet. But this quiet feels different. Not empty, full, not simple, dense with meaning, like the air before a thunderstorm or after a symphony. And in this pause, this gentle hush before sleep, you finally ask the most intimate question of all. What if you are not in space-time, but a ripple of it? What if everything you are, your body, your breath, your memories, your voice in your own head, is not housed inside reality, but is an emergent event within it? Not a passenger riding through space-time, but a pattern it produces, a momentary vibration in the very fabric we've spent this whole journey trying to look beneath. It's a wild thought, and yet increasingly plausible. Many of the theories we've touched on, string theory, loop quantum gravity, spin networks, entropic gravity, ADS/CFT, even causal set theory, they all hint at the same possibility, that what we experience as space and time are not primary elements of the universe. They're effects, consequences, emergencies, and you're not built from matter moving through space. You're built from interactions, from information updates, from transitions in a network of relationships so complex and so ancient that it stopped caring about coordinates long before you were born. Let's try a gentle analogy. Imagine space-time as a calm lake, smooth, stretched wide, still, and every vibration on that lake, every ripple, is a configuration of energy, of meaning, of you. You aren't floating on it. You are the movement itself, a brief localized swirl in an otherwise indifferent sheet. And just like a ripple, you don't have an edge. You don't contain yourself. You're not in a location. You define a location for as long as the pattern lasts. When it fades, the lake remains, but that shape of you, that precise interference pattern of space-time, energy and thought, it ends. But perhaps not the information, not the structure. If the universe is built from data, if information is conserved even when space-time melts, then you, as a ripple, may be archived in the deepest layers of the cosmos, not as a soul, not as a ghost, but as a configuration that once was, and may be again. Here's the weirdly comforting thing. If you're a ripple in the hidden layer, you're not outside of it. You're not some visitor trying to peek beneath the veil. You're the veil moving. All those theories, all those networks and strings, all those holographic projections and quantum vibrations, they aren't separate from you. They are you. Not just the framework around you, the structure through which you happen. Historians and physicists still argue whether this shift, from thinking of the universe as a thing you're in to a process you're part of, is just a semantic trick or a genuine metaphysical revelation. But either way, the result is the same. You are not small, you're not separate, you're not watching reality from the outside. You're a phenomenon in space-time's deepest grammar, a fleeting phrase in its ancient looping sentence. And the fact that you can even wonder about your place in it, the fact that you can look beneath space-time at all, and it means that you're made of the same logic you're chasing. So tonight, as your thoughts dim and stretch and settle into patterns even you won't remember come morning, know this. There is no final layer, there is no ultimate flaw. There is only depth and the human urge to dive into it. Maybe you're just a ripple, but you are this ripple, here, now, perfectly structured, perfectly temporary, perfectly part of it all, sleep well, space-time. One of your ripples is ready to dream. You've come a long way. Not in distance, not in time, but in thought. Across black holes and bouncing beginnings, quantum knots and cosmic holograms, you've followed the trembling threads of reality deeper than most ever dare. And now the questions are quiet. Still there, yes, but settled. Softer. The edges of the universe no longer demand to be solved. They just glow. Like the fading shimmer of water after the stone sinks. Like stars that haven't been named yet. You don't need answers tonight. You don't need diagrams or certainty or one final explanation to hold on to. Because you've already touched something deeper. The sense that beneath space-time, beneath physics and feeling, beneath the scaffolding of what is and what was and what will be, there is a pulse, a rhythm, a story that tells itself not in words but in waves. And tonight, you are part of that wave. You always were, so let your breath slow, let your muscles soften, let the questions you carry evaporate like steam rising from a calm, warm lake. No more need to push. The thinking can wait. The understanding will come when it needs to, and until then, this is enough. You are enough. The hidden layer holds you, ripple. The logic cradles you, question. And space-time for now folds gently around you like a lullaby with no end. Sleep, dream, drift. You've earned it.